Here I will talk about compact and stable posterior mouth contrast Jones-matrix OCT for pigment, flow, and fibrotic tissue imaging, and I'm Yasuno from Computational Optics Group at the University of Tsukuba, and this study is in collaboration with Tomei Corporation and Tokyo Medical University. This talk aims at introducing our recent development of a clinical research-grade Jones-matrix OCT prototype, and I'm also going to show its clinical utility. You are maybe curious about what is Jones-matrix OCT. The Jones-matrix OCT is an extension of OCT which measures the three-dimensional distribution of the Jones matrix in a sample. But the Jones matrix is purely physical and mathematical quantity, so maybe it is out of your interest. But Jones matrix possesses all of the optical property of the tissue. So once we measure the Jones matrix, we can compute a lot of clinically useful images from this Jones matrix. It might include a high-sensitive OCT image and also local scattering image. By applying the phase analysis and time correlation analysis, we can compute flow contrast and OCTA. In addition, by applying polarization-sensitive processing, we can compute the birefringence image, which is known to be sensitive to collagen, and also polarization uniformity image, which is known to be sensitive to melanin. My group has been working for Retinal mouth contrast Jones matrix OCT for a long time. The first demonstration was in 2012, and in the year of 2013, we did the first clinical case measurement. In 2014, we applied this method for the investigation of exudative macular diseases. And in the year of 2015, we released the first clinical prototype, and this prototype is equipped with a function to measure the local birefringence of the sample. Since 2017, we did several clinical case series measurements, which include RP abnormality evaluation and a Vogt-Koyanagi-Harada disease evaluation. Last year, we released our second clinical prototype, which is a compact clinical prototype, and this is the main subject of this talk. How the compact Jones matrix OCT prototype is better than our first clinical prototype. To think about it, here I would like to compare these two prototypes. The first clinical prototype that was released in 2015 had the footprint of 100 cm times 55 cm. The one improvement we did to the prototypes is introduction of encased compact polarization components. Owing to this introduction, now anything about the OCT are packed in a single scanning head. So the footprint becomes as small as 55 cm times 42 cm. The second improvement is the introduction of temperature-stabilized fiber components. Owing to these improvements, now we achieved a very good long-time stability of the device. How is the compact clinical prototype stable? To evaluate it, we operated the system without maintenance for more than 10 months. The first row shows the images taken after 2 weeks of the device installation. All of the image types show significant contrast. After 10 months of maintenance-free operation, we did the same measurement, and again all of the images show significant contrast. Here I also would like to explain how we can read the multi-contrast images, especially polarization-sensitive images. One of the polarization-sensitive image is polarization uniformity image. The polarization uniformity is known to be sensitive to melanin, so which highlights RPE and also choroidal stroma. The birefringence image is known to be sensitive to collagen, so collagenous tissue such as sclera is going to be highlighted. Before showing example cases, I would like to summarize the basic specifications of the device and its available contrast. The probe wavelength of the system is 1.06 microns, and A scan rate is 100,000 A lines per second. The axial resolution is 6.2 microns in tissue. These specs are equivalent to commercially available 1-micron swept source OCT. The sensitivity is 88.7 dB per polarization channel, but by using the coherent composition, it becomes equivalent to 94.7 dB. There are three contrasts available in addition to standard OCT. The first one is OCT angiography, OCTA, which is computed by using complex decorrelation algorithm. The second one is a melanin contrast, which was computed by using the degree of polarization uniformity algorithm, or in short, polarization uniformity algorithm. The third one is a local birefringence, which was computed by using a maximum a posteriori estimator. Let me show some example cases. We measured 29 cases, which include choroidal neovascularization and myopic CNV. In addition, we also scanned fibrosis and hemorrhage cases. The scan was performed with 6x6 mm raster scan protocol, and a single volumetric measurement was done in 6.6 seconds. The first case is choroidal neovascularization. In the OCT image, we see a hyperscattering material. In the OCTA image, we can find there is an abnormal blood vessel within this hyperscattering material. By checking the polarization uniformity image, we can find there is a defect of retinal pigment epithelium, and this finding is consistent with the finding in the near-infrared fundus autofluorescence. By checking the same region with birefringence, we can find a high birefringence. This might be the indicator of fibrosis. The second case is also an CNV case. In the OCT image, we see a huge hyperscattering material. Again, in this hyperscattering material, we can see an abnormal flow in the OCTA image. By checking the polarization uniformity image, we see several types of abnormality of RPE. It includes the thickening of the RPE and RPE migration, and also absence of the RPE. The birefringence appearance is not the same with the first case. Here in this second case, the hyperscattering material exhibits low birefringence. The last case is a case of myopic CNV. In the color fundus photo, we see a huge myopic conus. At this region, we see the atrophy of the RPE in the polarization uniformity image, and this finding is consistent with that in the near-infrared FAF image. In OCT image, we see a hyperscattering material. Within this hyperscattering material, we see an abnormal blood flow. In the birefringence image, we can find this hyperscattering material exhibit high birefringence, and this might be the indicator of fibrosis. Let me summarize the birefringence appearances of hyperscattering materials. In some cases, we see a high birefringence appearance. This might be the indicator of fibrosis. But in some other cases, the hyperscattering material exhibits low birefringence. This might be the indicator of non-fibrotic tissues, such as hemorrhage. The high birefringence appearance of subretinal material was found in all 14 cases of fibrosis and 2 of 9 cases of CNV, and also in 2 of 3 myopic CNV cases. Willoughby recently pointed out that the subretinal material can be a biomarker of AMD's anti-VEGF treatment. So, the classification of subtypes of subretinal material by using JM-OCT's birefringence measurement would be a useful tool for AMD treatment monitoring. Let me conclude my talk. Here in this presentation, I introduce a new compact and stable clinical prototype of Jones-matrix OCT. The Jones-matrix OCT revealed the tissue property of subretinal materials. The birefringence imaging will enable subretinal material classification, so the Jones-matrix OCT would be a useful tool for anti-VEGF treatment monitoring. Thank you for your attention.